Hi everyone, I'm Chandra Mohapatra, a graduate student at IIT Bombay, India. I'll be talking about multipoint evaluation in small characteristic and some of its applications. This is joint work with Vishwas Bhargava. He is a graduate student at Rutgers University. Sumanta Ghosh, he is a postdoc at Caltech, and my advisor Mrinal Kumar from IIT. Okay. Without any delay, let me get into the topic. So here is a fundamental question that we ask. So there is this given n-variate polynomial f over some field fq. So throughout this talk, I will be assuming the number of variables to be n and the input field to be fq, which has individual degree less than d, and bunch of given points alpha 1 to alpha m over this field fq. Okay, and this polynomial is given to us in the coefficient representation form. Okay. And the goal is to compute f of alpha 1 to f of alpha m. Basically, I want to evaluate f on all these bunch of points. So what's the input size? The input size is d to the power n plus mn, because the polynomial is given to us in the coefficient representation form, and each of these alpha is are like n length vectors. So here, basically, when we say input size, the input size means how many field elements are needed to represent the input, and that's roughly O tilde of d to the power n plus m. So I'm hiding some of the lower order terms in O tilde. Basically, when I'm saying O tilde throughout this talk, I'm hiding some polylog factor of the order of the higher order terms. Okay, so that's the input size. And what are the what are the strategies? So the trivially you can do it in order of m into d to the power n many field operations, because computing any one of these f of alpha I will take order of d to the power n many field operations trivially. So to compute all of them, it will take order of m into d to the power n. And to make the problem interesting, you can think like m to be some order of d to the power n. When m is of order d to the power n, then the input size roughly becomes order of d to the power n, but the trivial complexity becomes quadratic in the input size, and that's the regime where we're interested in. That there the problem becomes more interesting. Okay, so of course, a natural question would be to can we do faster? Can we do for a start? Can we make it sub-quadratic? Okay. Or do we know any special case, let's say univariate case, where we have some better understanding about this problem? So let's try to understand. Let's try to see what we know about the univariate case. So I'm just posing the same question in the univariate setting, and trivially you can do it in order of MD, many operations. And we know that when these evaluation points alpha 1 to alpha d are all dth root of unity, then I can use fast Fourier transform to compute it in some order of d log d. So it's nearly linear time in the input size, because here the input size becomes order of m plus d, and when m is of order d, then the input size becomes order of d, and this takes order of d log d. So that's nearly linear in the input size, and that's great. Okay, so what about any arbitrary set of evaluation points? Because when these alpha is are some structure, or like they are all d root of unity, then we can do better. We can do much better than a trivial thing. So we ask the same question for arbitrary set of evaluation points from the underlying points, from the underlying field. Okay, so Borodin and Monk in 1974 gave a nearly linear time algorithm which works for any arbitrary set of evaluation points. So if many arbitrary evaluation points are given to you from the underlying field fq, then actually we can do it in O tilde of m plus d. So ignoring some lower order terms, we can do it actually in nearly linear time in the input size, because here the input size is order of m plus d. Okay, so that's for the univariate case. So note that so for the univariate regime, this problem is like almost settled. We can do so. This algorithm actually works over all fields. So and it doesn't have any such constraint, and so this is nice. But we have a gap in understanding about this univariate case and the multivariate case. In the multivariate case, we are still trying to understand how to get our hands on all these things. Okay. Okay, so let me come back to the multivariate problem, and here I have represented compactly using this bold x, so that represents x1 to xn. Okay, so I have told you all this. So our wish is to compute this problem in nearly linear in the input size, because we already know for the univariate case there does exist some algorithm here, the Borodin and Monk's algorithm, that solves the problem in nearly linear in the input size. So we wish to do also, we also wish to achieve the similar set of complexity for the multivariate case. Okay, so the input size to the power 1 plus little of 1, that's O tilde of some divided to the power n plus m. So we want to evaluate in this much time. Okay, like we saw in the univariate case, when the input points are structured. So for example, when they were like dth root of unity, then we could do it in a much efficient way compared to the trivial complexity. So here also we ask the same question: can we do better for structured set of evaluation points? So if there is some structure, can we do better? So it seems like it is true that if the evaluation points, if the set of evaluation points are actually forming a product set, then we can actually do better, much better than the trivial thing. So let me first define what's the product set. What do I mean by a product set here? So basically, if you take subsets of the underlying field FQ in many subsets and you take the Cartesian product of those, that will form a product set. If I want to evaluate my polynomial, input polynomial on this product set, then I can actually do it efficiently. The input size, so basically when I'm saying efficiently, that means nearly linear in the input size. Okay, so a special case would be to evaluate fx on all points over the underlying field fq, all points, all possible points. That's basically saying evaluating fx over the whole grid fq to the power n, and the input size will be order of d to the power n plus q to the power n, and the complexity, the output complexity will be o tilde of some d to the power n plus q to the power n. That's why we can, this is something that we are saying that we can do it efficiently. Okay, okay, so but we are not just interested in some structured set of evaluation points. We are interested in arbitrary evaluation points. And what we know about arbitrary evaluation points, up to 2004 we didn't know anything about even for the bivariate setting. Okay, in 2004 Nusken and Ziegler gave a fast multivariate multipoint evaluation for bivariate polynomial. So they consider the polynomial bivariate polynomial while the individual degree is at most d, let's say less than d, and there are d square many evaluation points given to you. So basically the input size becomes order of d square, and they solve it in order of d to the power 2.667, something like that. So actually, so it's not nearly linear, but it's a great start because it does much better than the trivial complexity. Okay, their algorithm actually generalizes to the multivariate setting, but again, in the multivariate setting also, it's not nearly linear in the input size. But it's a great start. In 2008, Umans gave a nearly linear time algorithm first time. So this is the first, as far as we are concerned, is the first nearly linear time algorithm for the multivariate evaluation. Okay, but he had few constraints, like the number of variables and the field constant. The characteristic of the field should be upper bounded by d to the power little of 1. Okay, in the same year, Kedlia and Umans came up with another follow-up paper in which they removed this field constraint and it works over all finite fields. Okay, but the variable constant, the number of variables constant, was still there. Again, it is a nearly linear time algorithm. And till now, we didn't know, as far as we are concerned, we didn't know any progress in this area. I mean, in this problem. And so what we prove is like over a finite field fq of characteristic p for n varied polynomial of individual degree less than d and m many evaluation points given to us, then it takes time m plus d to the power n to the power 1 plus little of 1 and some lower order terms. So again, this is a nearly linear time algorithm. And again, we get some field constant, that is the characteristic has to be upper bounded by d to the power little of 1. Along with that, our field should not be very, very, very large. So for all practical purposes, we can handle large size fields, but it should not be too large. So it is basically upper bounded by some exponential fixed height of exponential tau or nd. Okay, so we are getting some iterative log in our algorithm. That's why in this sort of bound we are getting. Okay, so at this point, let me tell you the algorithm type that we deal with. So basically, there are two types of algorithm in this context we deal with. So one is algebraic, the other one is non-algebraic. So we say an algorithm is algebraic if it uses all the operations that can be mimicked or that can be transformed as basic field operations over the input field. Okay, so or the underlying field. then it is algebraic. If I can't do so, then it is non-algebraic. Okay. Okay, so basically why we're interested in algebraic, so mostly we are interested in algebraic algorithms because algebraic algorithms are like canonical way of, representing arithmetic circuits. So basically if you have some algebraic algorithm, then I can basically transform this algorithm to an arithmetic circuit, because arithmetic circuit uses all the basic underlying field operations. So if the algorithm also uses basic field operations over the underlying field, then over the input field, then I can succinctly represent that as an arithmetic circuit. So if you do not know what's an arithmetic circuit, then you can just ignore this point. So basically we are more so we would like to have our algorithm to be algebraic. That's more interesting. Okay, so here I compare the results of Uman's, Kedla Uman's, and our work. So you can see the number of operations is roughly same up to lower order terms in all of these works, though, so they are all nearly linear in the input size. And the type of algorithm is like the Uman's algorithm, the first algorithm where he was getting this field characteristic constant as well as the number of variable constant. That algorithm was algebraic. So basically it uses all input field operations, basic operations over the underlying given field. Okay, but in case of Kedle-Eumans, the algorithm was non-algebraic. So they basically removed this constant that the field characteristic should be small. So they gave it over any finite field. Maybe the field size is not too large in their case, but they did it at the expense of making the algorithm non-algebraic, because their algorithm actually they transform this problem to some other domain, they solve there, and they again come back to their field. So they are not doing all the basic field arithmetic things. That's why that becomes non-algebraic. And our algorithm again has some constants, such as again the characteristic has to be upper bounded by d to the power of 1, the field size should not be too large, but it again preserves the algebraic nature. And a significant improvement comes in the variable column, which is the last column. Note that in both Uman's as well as in Kedla Uman's work, the number of variables was upper bounded by d to the power of 1, and in our case we actually make it work for all n. Okay, so uh, that's a step towards making removing these constants one after another. And so this is it. And let me tell you why people study mme. Okay, so this multivariate multipoint evaluation, so it has some nice connections with univariate factorization and to modular composition. Actually, multivariate multipoint evaluation is very close to modular composition problem. So modular composition problem is this problem. So imagine there is this n-variate polynomial is given to us. So let's say that is f. F is an n-variate polynomial, and I have like g1 to gn many univariate polynomials, and there is another polynomial hx. So I want to compose f with gi's. So basically I want to compute f of g1 g2 up to gn. Then I want to mod out this with some hx. Okay, so that's the modular composition. So I want to efficiently compute this modular composition problem. So this modular composition problem is very much related to this multivariate multipoint evaluation. So if I can improve the complexity of one, then I can improve the complexity of other. So the complexity wise they are similar. And this modular composition problem has some implications towards the univariate factorization complexity. That's why the Kedle Human's paper, basically they improve the modular composition thing to make the univariate factorization over finite fields fast. Okay, and they also gave some other bunch of applications. Interested readers are requested to look at that paper. And we have two more new applications. One is we gave a data structure conjecture. We gave a data structure related result where we give a counter example to Milterson's conjecture. So, and we also give upper bound on the rigidity of Vandermonde matrices over some mild conditions, field conditions such as the field size should be like quasi-poly bounded, and it must have small characteristic. Okay, so I won't have much time to talk about these things, even to define what is matrix rigidity and what's this data structure problem or Milterson's conjecture. So interested, again, readers are requested to look at a paper. Okay, so let me give you the proof overview. So this is the main result, and you can stare it for a bit, and note that so this is not a one-shot kind of algorithm. Rather, we go via three versions. So we give one version of our algorithm that may not be quantitatively great. Then we again polish it a bit and we go to the next version, and where we again polish it a bit to go to the third version. So we have basically three versions of our algorithm. In the first version, actually the first version essentially carries all the essential ideas of our algorithm, but then it can be slightly polished to get better bounds. That's the overall thing that we're trying to do. So it's a three short thing. So in the first algorithm, we are getting this complexity, which is m plus b n p log q to the power n and some lower order terms. Note that when this n, p, and log q are of some order of d or something like that, then that will cause problem, because that will make the whole sense of making this algorithm as nearly linear in the input size won't be possible. So that's why we are saying that this n, p, and log q are strictly lesser than d to the power little of 1. Then the algorithm, the complexity of the algorithm 1 is nearly linear in the input size. That's why these constants are coming. In our second algorithm, we use some extra trick to remove this n to the power n thing, and we reduce that to 4 to the power n. And when the degree is say more than a constant, something like little of omega of 1, then this is interesting, because this 4 to the power n factor is much smaller compared to n to the power n. So basically, that's how we remove the variable constant here. But again, p and log q cannot be comparable to d. Otherwise, again, that will ruin the nearly linear time algorithm idea. Okay. In the third algorithm, we again polish the second algorithm a bit, and we improve the 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 the, the field complexity. Okay, so the field dependency. So in the second algorithm, you can see the field dependency was log q, and in the third one, it's some iterative log. And because we use some sort of recursion to improve the field dependency, and that's the final algorithm. But I will only talk about the first algorithm, which essentially carries the main proof idea, and that's it. That will be the end. Okay, so let me talk about the proof overview of our the vanilla version of our algorithm, the algorithm 1. So there are two phases in our algorithm. One is the pre-processing step, and the other one is the iteration phase. So the pre-processing phase basically contains so in the pre-processing phase, we pre-process, we store some of these informations without even looking at what are the evaluation points. Okay. In the iteration phase, when we see these evaluation points, we iterate one after another for all these evaluation points. Okay. Okay, so let me tell you what we do in the pre-processing step. So this is the input field, right? So this FP is the base field, and Q is, we are saying, P to the power A. So A is the degree extension. So this is the input field given to us. Okay, now we are interested to compute a subfield of it, which is FP to the power B, such that P to the power B, this field has some reasonable size, which is like A, D, and where A is again this field extension, this original FQ is P to the power A. Okay. And why such a field must exist? We are assuming that B divides A, and that's why it exists from the elementary field theory. But the thing is, so note that this B dividing A should not be considered as if some real constant here. Rather, we are just assuming it for simplicity. If B doesn't divide A, then you can use some sort of field extension and you can work over it. So it's not really a constant. I'm just assuming it for the sake of simplicity. Okay, so you can always find a subfield F to the power B, which is of some reasonable size ADN. So you don't need to worry about ADN, how we are getting ADN. This is some parameter setting. We will see later. Okay, you compute this subfield and you compute all the points that are possible over this subfield F to the power B. Basically, you consider the grid F to the power B to the power N. So basically, you consider all points possible where I can evaluate my polynomial F, and I am evaluating F on this grid. That's my pre-processing step. So basically, you find a subfield of the given input field of some reasonable size. Then you consider the grid structure. So this F to the power B to the power N is a subset of points from all sets of points over FQ to the power N. and we are trying to evaluate this polynomial fx over this grid f p to the power b to the power n. Okay, that's the pre-processing step. We have not yet seen any of these evaluation points. Without seeing any of these evaluation points, we have done this. Okay, now we see any point alpha. So where this alpha can lie? Alpha can lie in any of these, anywhere in this region, in the whole grid. And if it lies in f p to the power b to the power n, then it is not interesting because we have already evaluated our polynomial on this grid. So let's say it lies somewhere in this region where we have not evaluated our f. So these green points are basically indicating that we have already evaluated this green dots, our polynomial f on eta for any point eta. Let's say this point is alpha. So what we want to do, the goal is, we have already pre-computed something. We have some prior information with us and we want to use this information to compute f of alpha. The idea is to pass a curve that passes through alpha as well as too many points in this nicer region, this grid from f p to the power b to the power n. Okay, if so basically we have already evaluated our polynomial f on these set of points, and so basically we have many informations about this curve. When this curve passes through many of these points, so we are saying that we have informations about this curve, and we use this local information to compute f of alpha. So without delay, let me tell you how to construct this curve. So you just represent this alpha, because alpha is some point from f p to the power a to the power n, and any element from f p to the power a can be represented as a degree a polynomial over the base field fp. So that's the way I'm representing alpha as some beta 0 plus beta 1 y up to beta a minus 1 y to the power a minus 1. So all these beta j's are some f p to the power n, because alpha is an n length vector. So you basically represent each of these coordinate as a degree a polynomial, and that looks like this. Okay, and the the curve you define is basically just replace this variable y with t. Okay, we have done nothing. Is just you find this representation of alpha over the underlying field fp, and you replace y with t. Okay, and we are saying all these things we can do efficiently, finding these beta i's and computing the subfield, what we did in the pre-processing step. Also all these steps are efficient, we can do it efficiently. Okay, define this curve g of alpha of t, and note that it is immediate that if I say t to y, then that will give you alpha. Okay, okay, but here is this interesting thing, that if I say t to any gamma, where gamma is in the subfield f p to the power b that we have computed in the initial step, then g of alpha of gamma is always in this nicer region, in this green dot region. Okay, and that's not hard to check. Once you see this, then we already know that evaluation of f on all these grid points. Okay, and that is helpful, because once I restrict f to this univariate polynomial g of alpha of t, then I can say that each time I set t to some gamma, then that will give me essentially what that evaluates to. So let's say if I restrict the polynomial f to this curve g of alpha of t and call it h of alpha of t, and I set t to some gamma from f p to the power b, then I know that what g of alpha of gamma will compute is a point in this grid, and I already know the evaluation of f on this grid, and that's why I know the evaluation of h of alpha and alpha on all these points from f p to the power b, right, using this pre-computation step. So what's the cardinality of this set? This cardinality is essentially p to the power b. For all these gamma, I know what will be the evaluation of h of alpha. And what's the degree of this univariate polynomial? Note that h of alpha of t is a low degree univariate polynomial, because g of alpha of t is a degree a polynomial. Let's say a or a minus 1 polynomial, and f is like a dn degree, total degree dn degree polynomial. So the total degree will be like a into d minus 1 into n polynomial. If I know more than adn many evaluations of h of alpha at some gamma, then I'm done, because I can interpolate this polynomial and I can essentially get our handle on this polynomial, this univariate polynomial, low degree univariate polynomial h of alpha of t. So as its degree is at most, h of alpha of t's degree is a into d minus 1 into n. So I am saying you pick some b, the smallest b, such that p to the power b is greater than adn. So in the initial state, in the pre-processing step, what we do is we pick the smallest b such that p to the power b is strictly greater than adn, and we we do the pre-processing thing. Now we already know the evaluation of h of alpha at p to the power b many points, which is strictly greater than ADN, and that's more than enough information required to interpolate h of alpha. Once we interpolate h of alpha, I just set t to y, because h of alpha of y is basically f of g of alpha of y, and g of alpha of y is by the nature of the corp, we know that that's alpha. That's why it will give you f of alpha. Okay, this is some nice picture, and whatever I said in the graphical way of explaining the algorithm, that's I have written it here. So basically, this is the pre-processing step. This is the iteration phase. And going forward, so this is whatever I said for the algorithm 1, and to get our handle on algorithm 2, what we do, we polish it a bit further to work, so in the pre-processing step in the algorithm 1, we are basically evaluating our polynomial on the subfield f to the power b. In algorithm 2, we actually not just evaluate the polynomial, but we also evaluate its partial derivatives on this subfield, and we collect more information about this polynomial in the pre-processing step, and that helps us to remove this variable constant. Okay, roughly that's the idea. And in the third algorithm, going from the second algorithm to the third algorithm, we carefully analyze the bottleneck where the field dependency is there, and we use some sort of recursive nature of this algorithm to recursive nature of this problem to get our handle on the field dependency. So we improve it recursively, and that's how we are getting some iterative log factor in the field dependency. Okay, so that's it for now. So if you have any remarks, queries, or questions, please feel free to connect me offline, online, whatever feels suitable to you. Thank you.